Okay, I'd like to finish up section 5.3 now. We're talking about exponential functions, and I guess the next thing I wanted us to look at would be solving some exponential equations. Now we're going to do some more of this later on in the chapter, but so this is kind of a preview, but there is more to know type thing. In these examples, we're going to be using a property that says if a to the u equals a to the v, and u and v are expressions involving x, a is the base of an exponential equation. As long as the bases are the same, you can remove the bases and set the powers equal. Okay, that is going to be the first thing that you'll want to think of just in general when solving an exponential equation. So like here, if I want to solve this equation, the plan would be to try to get the same base. Now I can do that, I just have to think, okay, 3 to what power would give me 81? Because I can get base 3 on both sides. Well, 3 to the 4th is the same as 81, so where I see the 81, I'll replace that with 3 to the 4th. That way I've got the same base 3. I can remove the 3's and set the powers equal. And so now I'm looking at 3x minus 2 equal 4. That puts me back on familiar ground because now I don't have these, x in the power anymore. Add 2 and divide by 3 and you get x equal 2 as the solution. Okay, now like any other equation, you can check your answer if you want. If you're comfortable with the algebra, though, there's no reason to be doing that for these equations. You won't have extraneous solutions. If x is 2, let me just quick check. 3 times 2 is 6, minus 2 is 4. 3 to the 4th, yeah, that's 81, right? Because I had to use that rule there in the process of solving. So x equal 2 would be correct. Here's another example. So suppose that we want to solve this equation for x. Now, I want to try to get the same base on both sides, but 32 is not a power of 4. Okay, so in this problem I'm going to have to work with both sides. Now, 4 and 32 are both powers of 2. I know 2 squared is 4, and 2 to the 5th is 32. So I'm going to try to get base 2 here on both sides. Law 3 on that list of laws of exponents in the previous video would say that you're going to multiply the powers on the next line. Make sure that you distribute 2 into the two terms there. Also distribute 5 into the two terms. Okay, now that I've got the same base here, base 2, I can remove the 2's and set the powers equal. So we have 6x minus 2 equal 5x plus 10. If you then subtract 5x and add 2, x equal 12 would be the solution to that. The point of this problem would be to say that, sometimes you got to work with both sides and changing the base to make them the same base. Here's another example. Okay, I'm solving this equation for x. Now e is the number e. We talked about that in the last video. And now an equation like this wouldn't be so bad in solving for x as long as we're using our laws of exponents. I'm going to keep the left side as is. E to the x squared is the same as e to the 2x. Okay, and then I'm multiplying that by 1 over e cubed. Well, that's the same as e to the negative 3rd power using law 5 on that list of laws. Law 1 then would say that in multiplying, if you keep the base and add the powers, you get e to the 2x minus 3 here on the next line. So now I've got the same base e. I can remove the e's and set the powers equal. If I then add x squared to both sides, then now I'm looking at a quadratic equation. And so now I'm back on familiar ground. We did lots of things with quadratic equations in Chapter 3. Knowing that this is a quadratic means that, of course, the next thing is to factor. This one will factor nicely. And when you set the factors equal to 0, you would get x equal negative 3 or x equal 1 as the solutions to that equation. Okay, here's another example. Solve for x. Now, sometimes you got to be a little creative with it. Okay, at least at this point. I still want to try to get the same base on both sides, and I can do that. I can get base 5 on both sides because I know anything to the 0 power is 1. 5 to the 0 would be 1. And so where I see 1, I'll write 5 to the 0. That way I've got base 5 there on both sides. I can then remove the 5's and set the powers equal. If we add 3x and divide by 3, then we get x equals 3 as the solution to that equation. Okay? Now, again, this is like a preview of things to come. All right? I mean, in all these problems that I showed you, we were able to conveniently get the same base on both sides. Now, like if in this problem here, suppose I wanted to solve 3 to the power 3x minus 2 equal 82. Well, then the problem becomes more difficult because 82 is not a power of 3 like 81 was. Okay, that's not a problem that you guys know how to solve at this point, but you'll know how to solve it later on in the chapter once we talk about logarithms. Now, I have attached a worksheet there on the notes that are on Blackboard. Here's the worksheet that I would like you to look at. I would have given this in class. And this is just some problems that I'd like you to solve each equation there. And on the next page, I've got all the answers to those equations. So go ahead and try those on your own, and make sure that you can be able to solve these equations here. Of course, email me or contact me if you have any questions on that. Okay. Now, in all these equations, you're going to be trying to get the same base on both sides. That's going to be the plan. Okay. The next thing that I wanted us to look at is just very briefly some examples of exponential equations. We're going to be doing more of this, exponential applications. We're going to be doing some more of this later on in the chapter because there is more to know, like I said. But this is just to, give you at least some applications based on what we've talked about already. One application is working with compound interest. Compound interest is interest earned on principal that is reinvested to earn additional interest. So it's money that you have invested that you're going to let that sit there, and you're going to gain additional interest on top of that money that you've already made in interest. We call that compound interest. The compound interest formula is given here, just the general formula. A is the future value. That's how much money you'll have later down the road by letting it just sit there. P would be the present value. We sometimes call that the principal, meaning that it's how much money you currently have. R is the interest rate. The interest rate is typically going to be given as a percent in these problems. And whenever you use the compound interest formula, you want to be able to convert that number to a decimal form. N is the number of times that you're compounding in a year. That will be given to you in the problem. So like if you're compounding annually, N would be 1. If you're compounding semi-annually, N would be 2. If you're compounding quarterly, N would be 4. If you're compounding monthly, N would be 12. If you're compounding daily, you would assume not a leap year, N would be 365. Okay, so it all revolves around a year for getting that value of N. Now, sometimes we calculate compound interest by using what's called continuous compound interest. Continuous compound interest just means that you're making the compounding period infinitesimally small. Or you can think of it maybe as compounding every second on the second type thing. Here would be the formula that you would need for when you're compounding continuously. Okay, and we sometimes call this the PERT equation. You want to be using the PERT equation whenever you're compounding continuously. A is the future value, just as before. It's how much money you'll have later on. P is the present value, how much money you have currently. E is the number E that we've talked about a little bit so far. R is the interest rate, and T is the time. The time is always in years, by the way. I didn't mention that in the last formula. Okay, so here's an example. I want us to find the future value if $10,000 is invested for 9 years at a 4.3% rate, compounded. Part A is quarterly, and then Part B is continuously. Okay, whenever you're compounding a finite number of times, you're going to be using the general formula for compound interest. That's the first one that I wrote down. Okay, so if I'm compounding quarterly, that means that 4 times in the year, I'm going to gain additional interest on top of the money that I've already made. I currently have $10,000, that'd be the p-value, and I'm going to multiply that by 1 plus, the rate is at 4.3%, 0.043 would be that percentage there converted to decimal form. N is 4, I mentioned, since we're compounding quarterly, and T is 9. I want to know how much is going to be there 9 years down the road. Okay, so then at this point, I would then go to the calculator. 4 times 9 is 36. That'd be the exponent. And I got the 84 model here. If you type in 1 plus 0.043 divided by 4, I'm getting 1.01075. I'd want to use all the digits on the calculator if possible, because I want this to be as exact as it possibly can. Okay, if you round too early, like if you call this 1.01, you're probably going to be pennies off, or in some cases you could be hundreds of dollars off if you've rounded way too early. So be careful about that. Okay, I wouldn't do any rounding until the very end when you round to the nearest cent. Of course, you're working with money, so there shouldn't be any issues about where to round. Go nearest cent anytime you're working with money. Okay, so now with this number, I want to raise this to the 36th power, and then I'm going to multiply by 10,000. And so it looks like I'm going to have $14,695.18 9 years down the road. Okay, part B is if we're compounding continuously. Since we're compounding continuously, I would be using the PERT equation. P is $10,000, and I'm going to multiply that by e to the RT power. R is 0.043, T is 9. 0.043 times 9 is 0.387. And so how I would type this in is I'd say, okay, here's e to the power, 0.387. And then hit enter, and then you're going to multiply by 10,000. And we're looking at $14,725.56 then as the amount that we would see later down the road then. Okay, now I got to be honest. I have never ever seen a bank offer interest compounded continuously. I think that what we just did here in Part B is sort of a silly calculation because we just don't see that in the real world. I mean, no bank that I know of is going to give you money every second of the day forevermore, okay? And that's what compounding continuously means. I mean, usually if you're investing money, you know, a couple times a year, maybe once a month, you'll get some interest. You're certainly not going to see interest every second of the day. That magical bank just doesn't exist, okay? So while the PERT equation is not really a practical formula for investing money, it's actually a super, super important formula for looking at how other populations grow over time or get smaller over time. A better example would be to talk about the population of the world. The population of the world is continuously growing, okay? Continuously is a key word that I mentioned. So, you know, every second of the day we have thousands of births happening all over the world. So if I were to study the population of the world and how that's changing, like, it would make the most sense to be using a formula that resembles the PERT equation rather than this other one over here. Okay? I was going to do 2 more problems in the book next. On page 435, I liked problem number, let's see here, it's problem number 46. Where it says the population of California was about 37 million people in the year 2010, and it's increasing by 1% each year. Estimate the population of California in the year 2020. Okay, now the population of this state is continuously growing. Okay, so it makes sense to be using a formula that resembles the PERT equation. Okay, since it's a continuous thing. There are 37 million people in that state in the year 2010, and so that would be the P sub 0 value. P sub 0 would be the current population at time 0 P would be the population at time t. Now the population of this state is increasing at a 1% rate, therefore R is 0.01. T is the time in years. So this formula that we've created would be the formula representing problem 46. Now notice how this is really just the PERT equation. It's just instead of A, I'm calling it P of T, because I'm using function notation. Still, it's the PERT equation though, essentially. Okay, now I want to know the population of this state in 2020. T is the time in years since 2010. So it's been 10 years since 2010, and therefore I would just simply plug 10 into the function and simplify. I've done that. 0.01 to the 10th is 0.1. Just slide the decimal point to the right 1 unit. And then you're going to type in e to the 0.1, whatever that is, multiply by 37, and that's how I'm getting 40.9. Be sure that you include million. There's not, roughly 41 people in the state of California. There's roughly 40.9 million people in the state, or at least that would be the estimate in the year 2020. Okay, problem 122 is another problem that I wanted to show you here. So we're just going to do part A in problem 122, where it says sometimes after a patient takes a drug, the amount of medication, A, in the bloodstream can be modeled by the equation that you see there, where A sub 0 is the initial concentration in milligrams per liter, R is the hourly percent decrease in decimal form of the drug in the bloodstream, and T is the elapsed time, which is in hours. Suppose that a drug's concentration is initially 2 milligrams per liter and that R is 0.2. Part A, find the drug concentration after 3.5 hours. Okay, so I've got this set up here. Here's the equation, or the function that was given to us. They said assume that A sub 0 is 2, so a patient is injected with 2 milligrams per liter of this stuff. And of course, as time goes on, there's going to be less in the bloodstream. Okay, R is 0.2. They told us. And now we want to know how much of the medication is in the bloodstream after 3.5 hours. So that would be just another plug it in and simplify. Okay. Negative 0.2 times 3.5 is negative 0.7. And then if you type in e to the power negative 0.7, hit enter, and then whatever that is, multiply by 2, you would have roughly 0.99 milligrams per liter of the medication still in the bloodstream after 3.5 hours have gone by. Okay, so these are just some examples of some applications of exponentials. We'll be doing some more of that later on, like I said. We'll go ahead and stop here though now. At this point, I'm now done with section 5.3, and so the homework is on page 434. Be sure to look at those problems when you get a chance.